Welcome to Physics Lesson 8, Total Energy, the law of conservation of energy. Please open your booklets to page 56. Okay, the law of conservation of energy states that energy, like matter, can neither be created nor destroyed in the universe. It can only be converted from one form to another. Examples include chemical energy being turned into mechanical energy, kinetic into potential energy, or thermal into mechanical energy. We can use this idea to solve some interesting physics questions and really start to go next level. In your booklet on the top of page 57, please write down this basic idea. And the idea is telling us that the total energy in a system before a transfer of energy is equal to the energy after that. What does that mean? We're going to get into it right here. Just copy that down. Okay. So what we're saying is that before something happens in the world, the potential energy plus the kinetic energy will be equal to the sum of the potential energy and kinetic energy after that happens. So little ninja jumping off the roof, we have like before or after the jumping's happening, the energy in the world still exists and it's the same on either side. Copy this down too, please. Okay. So due to this law of conservation of energy, we can really do some amazing things with these physics concepts. So right on the middle of page 57, let's jump into an example. So imagine a roller coaster cart as it travels along the track. As it's going up the mountain to the drop of doom, it's increasing its potential energy, right? It's going up in the air and there's more room for gravity to act on it. So it's increasing its potential energy. Then at that maximum point, at that highest point, its maximum potential energy will equal the total energy in this system. Okay, then boom, it goes over the top. Ah! As this roller coaster is about halfway down, we're going to be able to say that it's using, like, there's half of the potential energy left and it's using half of the kinetic energy because it's halfway. So it's got half of both. It's half in action, but it still has energy in that potential stage. So what we're saying with this equation is that the energy total is equal to that potential energy, EP, plus the kinetic energy, EK. So then as we get to the bottom, that thing's zooming along, and we're going to say that at its maximum speed right here, because this is the fastest it's going to be going right when it gets to the bottom there, that the total of energy in the system is now just equal to the kinetic energy because there's no potential energy. It's at the bottom, right? All right, so what we're saying is when it's at the very top, we'll have its maximum potential energy, which will equal the total energy in the system. And at the bottom, when it's in that kinetic form, when that thing's just zooming along, its maximum kinetic energy that's being used is equal to what it was at the top. So that's this idea that it's always the same. The energy can't like disappear into nothingness. It goes somewhere. So in an equation, they're actually totally equal. Now, this concept is going to do some amazing things for us starting right now. Okay, middle of page 57. Let's just go through an example because, again, how can we possibly wrap our heads around this stuff unless we're doing it? So let's look at this question. A roller coaster, a 435 kilogram roller coaster, is sitting at the top of its first descent, which is 240 meters above the ground. Wow, that is a roller coaster. If the roller coaster is released and reaches the bottom of the track, how fast will the cart be going at the bottom? Okay. Okay, this seems doable. Let's just start with our old friend grasp and let's figure out what we know. What do we know? We know that the mass is 435 kgs. We know that the height difference between the top and the bottom is going to be 240 meters. And we know that the gravity working on it is always at 9.81 meters per second squared. Okay, so that's what we know. Now what's this actually asking of us? What's required? And it's asking for us, how fast will the cart be going at the bottom? So we're talking about velocity. I know speed versus velocity, whatever. We're going to call it velocity here. Okay? So what's the velocity here? So let's analyze this. Now, what do we know? We know that potential energy at the top of the big drop of doom, we knew what that was, okay? Or we know that is equal to the kinetic energy when it gets to the bottom and it's going super fast. So when we look back to last lesson, we can check and we'll recall, or if we don't, look on your cheat sheet. I put one on the main screen for us. But we know that EP, potential energy, is equal to mgh, and we know that EK is equal to half of mv squared. So we can say, knowing that they're all equal, we can say that those two are equal. Now, wow, we are going to have some magic with this. With this understanding that mgh equals half of mv squared, we can do amazing next level things in this world. So hang on tight, because this roller coaster, we're going over the cliff right now. Let's go deep. Okay, so let's fiddle around with this. We know we're looking for v, so we're going to try to isolate v. So let's get rid of that halfer. We'll multiply both sides by 2, because again, if we do the same multiplication on both sides, the equation still stays equal, so we're good. Okay, so we multiplied both sides by 2. On the right-hand side, the 2 got canceled out because 2 divided by 2 equals 1, and we can just get rid of it. Okay, and then we will divide out that m, and then we come up with this equation, and then we just have to end that. We can cancel out those little m's, and we come up with this fancy equation, 2gh equals v squared. And then, do you recall how to get rid of a square? That's right, a square root. Okay, so we've just isolated v. So what do we need to do now? We need to solve it. So let's just plug some numbers in there, and wow, let's show our friends that we know how to math this one out. This is quite the big number here, quite the big equation, but we'll just plug that into our calculator and wow, holy smokes, we just did some next level science. Way to go, team. So of course, last thing we're going to do, we just found out the velocity at the bottom there was 68.6 meters per second. Wow, what a fun roller coaster that would be. Okay, so we're going to paraphrase it just to make sure us and everyone knows what we're talking about. So we're just going to say if a 435 kilogram roller coaster travels down a 240 meter track, it'll be traveling at 68.6 meters per second when it reaches the bottom. Wow. Okay, take a minute, make sure you have this all written down. I know we just flew through that. The big point that I want you to get while you're copying this down is that EP equals EK is equal. And we can put those numbers in there, that potential energy and that kinetic energy. We can put those into these equations because we know that the total energy will be the same before and after. It'll just be whether it's, which portion of its potential and which portion of its kinetic after whatever activity happens. So with that knowledge, we can do ridiculous, fancy, next level things. And what we really have to learn here is to follow the process. To learn to write out these equations and then trust that process and then follow through with that process. Okay. If you need to pause it to finish writing down this equation, do it now. Moving on. Okay, bottom of page 57, we've got one more example for you. So let's go through this one together, and then you can get on your own practice work so you can really wrap your head around this amazing concept. Okay, so a 500-gram rocket is launched straight up with the initial velocity of 45 meters per second. How high will the rocket be when it slows to a speed of 3.5 meters per second? Again, what do we start with? Our old buddy grasp. Boom. What is this telling us? What is given? It tells us that we have the rocket at 500 grams. And again, we know that we have to change this into kgs, so we'll do that. And then we have an initial velocity of 45 meters per second and a final velocity of 3.5 meters per second, because this question is asking us what's going to be happening at that final velocity of 3.5 meters per second. And then our old buddy gravity at 9.81 meters per second squared. Okay, so what's this asking us for? How high will the rocket be when it slows to a speed of 3.5 meters per second? Okay, so it's this change in height that we're looking for. We're looking for h. Now let's just start plugging in equations. So again, the information that we have here tells us that at first we're just looking at kinetic energy. We're firing that thing off of the ground. The potential energy is irrelevant in the before our activity happens. It's all kinetic energy. All this kinetic energy is going into the rocket, or coming out of the rocket, and is shooting straight up into the air. So as it's going into the air, because it's working against gravity, we're building that potential energy of gravity. So we know that as the rocket goes up into the air, that potential energy is growing. At the same time, we know that the kinetic energy is dissipating. It's getting smaller, and it eventually, and it's slowing down. Okay, so we know that because of this law of conservation of energy, we know that everything on the left-hand side, the sum of that will be equal to the sum of the stuff on the left-hand side. So now with this equation, we can just plug our numbers in here. Okay, let's see what this looks like, because this is going next level. So we got this big half thing. We know that EK equals half of mv squared. And then we know that EP is mgh, and we know that that next EK is just the same thing, half of mv squared. But remember, and it's hard, you can't tell with this diagram, but maybe make a little note of it in your notes. On the left-hand side, we're talking about velocity 1. That's the mass is still the same, but the velocity is 45 meters per second. And then on the right-hand side, we're only going, that velocity is 3.5 meters per second. So that'll be the final velocity that we're talking about, because we're going to start mixing these around. So right now we know that we're trying to isolate h, and the h is in that mgh. So we're going to get on the right-hand side. So we're going to subtract out the final EK there, the half mv squared from the right-hand side. We're going to subtract from both sides, and then that'll give us, on our left-hand side, half of the initial mv squared minus half of the final mv squared equals mgh. Again, let's just keep working through this. Let's isolate h, so we'll just divide both sides by mg. That'll cancel it out on the right-hand side, and we'll have this big long equation on the left. Again, we're just trusting the process here. We know how to manipulate formulas now, so that's what we're looking at doing now. And they look super complex, but they're all built out of ideas that we know and that we can plug into. Okay, so we have this now. We've analyzed this. We've isolated h, and all the question is asking for is h. Okay, so what do we need to do? We need to solve it. We need to plunk a bunch of numbers in here. And this is going to be a long equation that we're going to want to show all our friends to impress them with our physics ability. So boom. We have this fancy equation. We're just going to plug it into our calculator. And bam, we come up with this nice simple number of 102.6 meters, which of course we're going to have to consider sig digs and put into scientific notation. And our final height here is 1.0 times 10 to the 2 meters. Now, of course, we'll have to paraphrase it, which we'll do. And that's simply stating if a 500-gram rocket launches straight up at a speed of 45 meters per second, it'll reach a height of 1.0 times 10 to the 2 meters when it slows to a speed of 3.5 meters per second. Please take a moment, pause it right now, and copy this down. Go through it, analyze it, figure out how this works. You can do it. Pause now. Moving along. We did it! There's one lesson left in physics. We can rock that one too. First place to start right now, if you're not too sure what's going on, is do the practice assignment on page 58. I want you to do that, and I want you to submit it to me. That is made in a way that it will help you build the capacity to do these super advanced questions. Thank you and good luck.